year before that, we had one for that was basically about using randomized email addresses for every single account. So I mean, if any kind of site or service got hacked, it would be very difficult, if not impossible, for them to actually identify your account in there because it's too much to look random. And nice way to do it. Okay, ready for the phone? Yeah. Okay, so we have with us Greg Zaverucha from Microsoft Research. From Microsoft Research.
Microsoft Research. Yeah.
Microsoft Research. Yeah, but don't be. You can help people do research out there.
Oh, well,
okay.
I mean, I do
We
some.
like researchers.
Okay.
Yeah.
Good. So I do some of both. Some research and some software development too. So.
Okay, so give it up for Brad.
Okay. Thanks, Per. So I'll be talking about password-based encryption today with I/O hardness, which is sort of a pretty loose term. Could mean memory hardness, but we'll see what I mean by that as I go. So why would you do this? Why would you encrypt with a password? I'm not encouraging people to do this more than they already are, but good key management is expensive. It's hard to do well. You need a place to store your key, and typically you want to back it up. And outside of enterprises, sometimes this isn't justified, right? Usually, when you're encrypting with a password, you're encrypting data to yourself. So you're the sort of the sender and the recipient. And it's overall, it's pretty usable, right? Most people can password protect a Word file, but if you ask them to encrypt something with PGP, they might not have such an easy time. So yeah, I'm not arguing we need to do this more often, but if you're going to do it, I'll present an idea that might make it more secure. So here are some use cases. So I mentioned Office documents, Word documents, zip files and PFX files can also be password protected. Password managers, encrypt a set of passwords with another password. Applications that secure data with like DPAPI or SQL Cipher are using, maybe indirectly, but password-based encryption. The tarsnap backup software has a utility to encrypt files with a password using scrypt. And the TrueCrypt disk encryption system uses password-based encryption as well. So, okay, how does this work? So I'll start with just a picture of normal encryption where there's a plain text at the top. We have an IV. That's a random value which changes for each encryption operation. Those two, together with keys, are inputs to the encrypt function, which outputs the ciphertext and the IV. So that's without a password. With a password, so typically a password and a salt go through a function called a key derivation function, and that's where you get your keys. And then everything else is the same. So there you have it. Usually we also want to authenticate our ciphertext using a MAC. So there's actually two keys that are derived. And we don't just encrypt, we authenticate as well. And there's a tag output at the end. And so some concrete examples here, you might use PBKDF2 for your key derivation. This is an iterated hash function. And AES CBC and HMAC are sort of examples of encryption and authentication algorithms. So the threat model for password-based encryption is different from having password hashes in a password file. So with a password file, exposure should be rare, let's hope, and it's a sort of a security event. Whereas with password-based encryption, the ciphertext is like sent over email or put on a share somewhere. So the hash, or the opportunity for a brute force attack is there right away, sort of by default. You're under attack. And changing the password is ineffective. You know, once the ciphertext is out there and the attacker sees it, you can't change your password in order to protect the plain text. So Jeff gave a nice talk about the threat model for password-based encryption last year at Passwords. So we'll assume that the attacker gets to see the entire output, right? The salt, the IV, the ciphertext, and the tag. Everything that you would need for decryption, the attacker gets to see this. So to do a brute force attack, so assume we just have the one ciphertext under attack. And we'll also assume that the attacker knows some of the plain text. So typically, you know, these files start with a standard header, so we'll just assume that the attacker either knows the header or can check that when he does a decryption, that the decrypted value matches the format, has the correct format. So for each password guess, he derives the candidate keys, does decryption of the first part, so say the first block of the ciphertext, and compares that to the known plaintext block. And if they match, then he'll continue decryption, decrypt the whole file, and maybe do some other integrity checks. So the cost for each guess is the work to derive the keys and decrypting one block. Okay, so what if the attacker didn't have this shortcut where he could decrypt one block and compare it to something he knows? So if we remove that, you can think of if we had encrypted random data. You know, the attacker would have to process all of it and then check in another way whether this made sense, this decryption made sense. So there the cost would increase by, so I'm using S for the number of blocks, but it would increase by a factor of S. And if it's a large file, this could be significant. So as I said, I call this I/O cost, so that maybe the file's on a disk if it's really large, or maybe it fits into memory and then it's like a memory cost. But the important thing is that the defender is already doing this work, right? When you have a memory hard KDF, this is sort of purely overhead. It's something that the attacker, to the defender, it's purely overhead. It's something he wouldn't normally do. Okay, so how can we do this? How can we force the attacker to process all of the ciphertext? And the tool is called an all-or-nothing transform. And so basically, we're going to encode our plaintext before we encrypt it. So the encoding is randomized. So here we have an encode and a decode function. There's no secrets here. There's no secret key. But the security property we get is that if you're given part of an encoded plaintext, you can't decode it until you have all of it. So if you only have the first block, that doesn't help you. If you're only missing a few bits, you might be able to brute force them. But if you're missing, say, more than 128 bits, you won't be able to do the decode operation. So why would somebody invent such a thing? This is an old idea. There's a good crypto paper from 1997 by Rivest, and his goal was to improve the strength of encryption using export keys, which is sort of similar to password-based encryption. It's something that you don't want to do, but maybe it's your best option or your only option. And export keys and passwords both, they're both weak. They both have low entropy. So later it was shown that OAEP, which is a padding mode for RSA encryption, is an all-or-nothing transform. And Rivest's transform is a special case of OAP. So I just chose to look at OAP in this work. So just to review how it works, our plaintext is input. We need two functions, G and H. G takes a random seed. It's a short seed, and expands it into something like a key stream. So you could think of G being AES encounter mode. And then you XOR this with the plaintext to encode it. So the encoded plaintext is Y. And then you need to somehow hide R, right? So that Y can't be decoded without it. So you hash Y and XOR it with R, and then append that to the end. And then so you can sort of convince yourself that that this works. So to decode, hash all of Y, XOR it with YR to recover R, and then recompute G and recover the plaintext. Okay, so we want to combine this encryption with this encoding. So if you start looking at this, there's a whole bunch of different ways to do it. I chose 3 and looked at them in detail. And so I'll just kind of informally present them here. And I wrote this up in a technical report with all the details. So I'll point people to that if they want more detail. So the first scheme is, I'm calling it MAC then encrypt, because that's what you do. You MAC the plaintext, then apply the encoding, and then encrypt that. The second one is encrypt and MAC. Here we encode, then encrypt, and then compute the MAC. And the third scheme is basic. It's the same as the second scheme, but we make a special choice for E, which lets us simplify OAP. So I won't present the third scheme at all here, but they're all in the report. So there's some detailed pseudocode, which I've also implemented to check that that it's correct. So I'll have the URL for that report at the end of my presentation. Okay, so comparing these schemes, AES GCM is what I had in mind as a kind of baseline for authenticated encryption. Like GCM, all 3 of the new schemes use a single pass for encryption, so they can work on a stream of data, which is nice. For decryption, you have to do 2 passes, and I don't see a way to avoid this, because if single pass decryption is possible, then after a constant number of operations, you can get that first plaintext block and check whether it sort of makes sense. But often we do 2 passes anyways, because we want to first check the MAC before doing any decryption operations. There's a nice blog post by Moxie Marlinspike where he calls this the cryptographic doom principles. So he shows some pitfalls of how security fails when you decrypt before authenticating. And then, another note is that these things are more complicated to implement. You have to implement the all or nothing transform, so you have to implement OAP, which may require new primitives that you weren't already using. And to get good performance, you have to interleave encryption with the encoding. So this to do this on a stream of data, you have to really interleave these things carefully. So now look at some of the costs of the attacks and the costs to the defender, right? Because we're doing more work. This encoding step isn't free and slows down things by roughly a factor of 2. So what do we get for this? What does this buy us in terms of resistance against brute force attacks? So it's kind of easy to do some estimates by just counting the CPU costs, the number of block cipher operations. So that's what I did to get a sense of the costs. So I'm still using S as the number of blocks. And so the attacker has to make one pass over the ciphertext in schemes 2 and 3, and 2 passes in scheme 1 before he can check whether a candidate key is correct. So I compared the ratio of defender and attacker work. So for every attacker operation, how many operations does the defender have to do? So here's a table from my write-up with some of the numbers. So you can see that the first scheme has the best ratio, so 2, meaning 2 defender operations for 1 attacker operation. And then it goes up to 4 in scheme 2. And then in scheme 3, which has this optimization I mentioned, it goes back down to 3. And they're all constant, whereas in AES, the attacker is doing 1 operation where the defender does S. So, or sorry, in AES GCM, that's the case. So the previous table kind of gives you a feel of how the schemes compare to themselves, but to look at some more concrete numbers, that'll give us a sense of how much extra work the attacker will have to do. And this varies a lot by the file size, right? That parameter S is really important. And also the work factor that you're using in your KDF. If that work factor is really large and the file size is really small, then it's effectively the brute force cost is dominated by the KDF, and it doesn't really matter what you do on the encryption step. So again, I'll make some rough comparisons here by counting the number of block cipher and hash operations. So here's a couple different file sizes. So 100K, a meg, 10 megs, 100 megs. So the number of AES decryption operations is there in the second column. So that scales as you would expect. Then I fixed the number of PBKDF2 iterations to 100,000. So that's about 200,000 hash operations. So then the attacker, without an all or nothing transform, just has to decrypt 1 block and do the PBKDF2 iterations. And then in the next column, it's the sum of the first 2 columns. So this is what the attacker has to do. And so you can see that when you get to about a 10 meg file, it's about 4 times more work. And so that's probably where it starts to make sense with these parameters. And of course, this is, it's imprecise. So it's just kind of back of the envelope. If the KDF, if your work factor changes, so what does that mean? So if we look at 50K iterations for PBKDF2, that's on the bottom of the table, then it's about 7 times harder with a 10 meg file. So you get more benefit. Okay, so going back to my examples, so SQL Cipher, which is an encrypted database that I learned about last year at Passwords, it encrypts each page of the database separately, and each page is pretty small. It's 64 AES blocks. So that extra decryption work that you're forcing the attacker to do is probably insignificant relative to the KDF cost. For other file types like Office documents and archive files, where they're usually larger, this probably makes sense and would improve security. But you do have to be careful because if you're encrypting multiple files with the same password, the attacker can pick the smallest one to do his brute force attack with. Okay, so that's all I have. So just to conclude, password-based encryption is still pretty weak. Don't run out and start using it unless you have to. And there are some scenarios where the third scheme I presented seems to give an improvement, but overall the idea needs more investigation, and especially from the attacker perspective. So I did some rough estimates and counted the number of crypto operations, but it would be nice to hear from an attacker who's familiar with sort of using GPUs as to whether this is, really going to make their life hard, or, whether there's an easy way that they can deal with this extra work. So the tech report is, that's the URL. There's more details there. You can email me or catch me later if you have questions. That's it.
And questions. Oh, it's Jeff. Wow. Haven't had a question before. Could you go back to the slide with your file size table? I was just a little confused about the ratio column. What's that the ratio between?
That's the total attacker with all or nothing transform divided by without.
Okay, because I think what might also be helpful or useful is to have the ratio between the attacker and the defender.
Yeah, I tried to capture that over in this table with this ratio. So maybe I should have called them different things because two different ratios, but
okay, thanks. I now understand the case.
Okay,
yeah, that makes sense.
More questions? Yep.
Hi there. So if I understand properly, OAP basically adds an extra factor n to the cost. Do you have any recommendations on logical groupings of data, like let's say tarbalized output, that would make sense and where this would really shine?
Sorry,
Basically, because the attacker can select the smallest file within the group and use that to perform the attack. Do you have any recommendations for data structures or logical groupings of the data that would make sense with this approach?
So I guess, yeah, you want to find a file size that's as large as your application can tolerate, right? And then kind of group things together. So, taking SQL Cipher as an example, the reason they encrypt small pages is so that they can do random access. They could encrypt the whole database, and then the brute force attack cost would go up, but there would be a trade-off in application performance. So it's it's going to vary by application.
More questions? Okay.
Supposedly there's not a stupid question, but this one may be one. Is it my understanding that you're using a static, as I call it, a secret key, or one manner of encryption? I came in a little bit late on what you're saying. What would happen if you were to use multiple, say for example, one-time pad secret keys, or more than one, if I understood this correctly? Have I confused your...
Are you, like, if you did two encryption, like encrypt first with one algorithm, then with the second? Is that...
Or someplace in between, change the secret key. I mean, multiple secret keys involved. This is something I don't know if anybody's ever thought of, but
yeah. So you can derive, multiple secret keys. They're all coming from the same password. So
that's what I mean. That one static location. What happens if you're able to change that static element and make it a one-time pad type of thing?
So then you have to manage the key, right? So
okay, so it's key management then.
Yeah, like really the reason people use password-based encryption is, I think, for key management mainly, right? So that you get a file on any device, and all you need is your password.
I'm just above that in thinking multiple. I'll call them secret keys, but whatever. Is that not correct? I mean, have you been there? Have you been thinking about anything like that? Has that been approached? Has anybody approached you with that kind of an idea? We ought to talk outside.
Sure, okay, yeah. Yeah, I mean, there are other ways to encrypt files,
Obviously.
and it all just comes down to managing the keys.
Okay.
So,
In the management, well, never mind, we'll talk outside.
okay, sure.
Thank you.
Yeah, thanks.
Okay, so thank you to Greg, and we'll just switch over to Steve Thomas. And one more time, thank you.